To find the shortest path from a point in space to a flat surface, the answer is physical and intuitive. You drop it straight down. In classical geometry, given a point and a diagonal line, the shortest distance is always a perpendicular line, intersecting at 90 degrees. But in data modeling, this intuitive distance creates a conflict with how we record information. To resolve this, we have to change our perspective on which direction distance should be measured. We can see the necessity of this change by looking at a standard laboratory experiment. This is a schematic representing Ohm's law, the principle that voltage equals current multiplied by resistance. We are going to use this relationship as the foundation for an experimental dataset. We can directly map this physical law to the standard algebraic equation for a straight line, y equals mx plus c. In this model, y represents our voltage. This is the output, or the dependent variable that we ultimately want to predict. Our x represents the current. This is the independent variable, the exact input that we physically control in the lab. The slope, m, represents the resistance of the equipment. This is the unknown variable we are trying to solve for. Finally, our intercept, c, is exactly 0. Since zero current yields zero voltage, any line we draw to model this circuit must pass directly through the origin. Imagine we've gathered raw data from the lab, and the technician says the equipment uses a resistor of exactly 1 ohm, or exactly 2 ohms. Finding the true physical resistance becomes a strict optimization problem. We have to evaluate whether a line with a slope of 1 or a line with a slope of 2 is the best mathematical fit for our physical observations. To account for the natural noise of a physical experiment, we took multiple readings rather than relying on a single test. Plotting experimental data, current on x, voltage on y, we recorded coordinates 1, 2, 5, 4, 7, 8, 8, 9, 9.87, and 10, 9. The 1 ohm hypothesis, model y equals x, threads through our data cluster. The 2 ohm hypothesis, model y equals 2x, angles steeper, missing the observations. Visually, it's obvious which line is a closer match, but we need a rigorous mathematical formulation to definitively prove which model is the superior fit. Isolating the reading where 7 amperes returned 8 volts against the y equals x model, the classical geometric habit measures error by dropping a perpendicular line to the model. But notice this perpendicular intersects the model exactly at an x-axis coordinate of 7.5. This measurement relies on an assumption that contradicts our experimental setup. It treats our physical input as if it were 7.5 amperes. In reality, our independent variable is fixed. We inputted exactly 7 amperes of current into the circuit, not 7.5. The only uncertainty in our experiment is the output voltage along the y-axis. The correct statistical question to ask is, for this exact unchangeable input of x equals 7, how far off was our predicted y? Measuring perfectly parallel to the y-axis, we drop straight down from our observed 7, 8 point to the prediction at 7, 7. This vertical distance is the true error, or residual. Evaluating the overall model requires measuring this specific vertical error for every data point. Statistical distance must remain strictly vertical. It is the only way to preserve the integrity of our known inputs while isolating the exact error in our predictions. The next objective is to combine all of these individual vertical residuals into a single comprehensive score that defines the model's overall fit. We can express a single vertical error as the observed value, yi, minus the predicted model value, mxi. The intuitive way to calculate total error is to simply add all these differences together. But simple addition has a critical flaw. Vector direction matters. Some points sit above the line, generating a positive error, while points below the line generate a negative error. If we sum these raw values, positive and negative deviations subtract from one another. A severely inaccurate model with massive errors could theoretically sum to 0, simply because opposing values cancel each other out. Taking a simple sum of errors is mathematically blind. It actively masks the actual magnitude of the model's inaccuracy. To solve the cancellation problem, we have to apply a mathematical operation that removes the negative signs entirely, squaring the error term. By squaring every difference, we force all errors, whether they occur above or below the line, to become strictly positive, absolute penalties. We can expand this formula to include our intercept, c, accounting for the full y equals mx plus c model prediction. Then we apply the summation symbol to represent adding up these squared penalties across every single point in the dataset. This complete equation is known as the sum of squared errors, or SSE. SSE provides a strictly positive metric. It captures the exact total of the vertical distances, revealing the true predictive error of any linear model. With our metric defined, we can return to the original physics problem and evaluate our two resistance models. Our first hypothesis, the 1 ohm model, yields an SSE score of 5.09. The second hypothesis, the 2 ohm model, returns a significantly higher SSE of 328.49. Since our goal is minimizing error, the math proves the 1 ohm resistor is the correct physical fit. In many real-world scenarios, however, we aren't just choosing between two neatly pre-selected guesses. The true power of the sum of squared errors comes when we use calculus to automatically tune our slope and intercept, hunting for that singular, unique line that strictly pushes the total error down to its absolute mathematical floor.